So I joined Tesla this summer. Previously, I was doing my PhD at Duke in Bayesian statistics. So this is going to be that Bayesian talk. A Bayesian at an ML conference. Surprised, not surprised. So I'm on the supply chain automation team, which is led by my friend and colleague, Dr. Charlie Freundlich. He is here in the audience. So if you have a resume, remember that face. I'm very excited to be giving this talk today because even if you don't agree with how we're approaching this problem, I actually think that if you're a data scientist, it's impossible not to get excited by the kind of data that we're working with. So, disclaimer, there's no real data here. Not allowed to, and this is a security for myself and everyone else. But the data is, it has the same sort of characteristics. So if you're in the room today trying to answer the question of whether to buy or sell, this is not a talk for you. Someone just left the room. Okay, so hypothetically, this is Tesla's outbound logistics network, okay? And what we're dealing with are finished vehicles that are constructed in the factory, and they then need to be sent to the customer. And they will go through some path in this graph. So from the different teams that I work with, I've began to learn that everyone has different terminology for this. So let's just decide on the language of graph theory and mathematics. So we have a set of nodes, and these nodes are indicated by the Tesla logos here. And these can be production facilities, they can be logistics hubs, or they can be service centers. And what we're interested in doing is we want to be able to forecast when the car is going to arrive at its final destination. So we want to provide an ETA that's useful for operations, but it's also something that we want to communicate to the customer. It's not the typical setup in graph theory and all those lovely graph theory problems where you have a set of edge weights and you want to do some algorithm. We don't have the edge weights yet. Actually, in fact, this is what we're trying to measure. We're trying to find out the transit times across an edge and also the dwell times within the nodes, okay? So what happens is when cars are finished, at least in North America, I mean, we're sending cars everywhere, but we're just going to focus on North America for this talk. They're put on a car hauler, and then they go off in the outbound logistics network. So a hypothetical one might look like this. Car is produced at the factory. It then needs to go to somewhere near Miami, and we want to be able to forecast when that car is going to arrive. So let me introduce you to the kind of data that we have to work with. Well, what we have are timestamps, and these are basically checkpoints within the car's journey. So we can see that actually this car went through 4 edges in our graph. And the in-transit timestamp is when the car departed the origin node, and the arrival timestamp is when it arrived at the destination node of that edge, or that leg. And we're using this to estimate the transit time. And then by looking at the next row, we're also using it to estimate the dwell time within these nodes, okay? Now, in logistics these days, you get timestamps from a lot of different sources. Typically, drivers will have a mobile app where they can mark things as checked in or checked out. Sometimes a worker at the hub will tell you that something has arrived. Someone on our side might do it. And also the carriers that we work with also have ways that they can enter in timestamps as well. So immediately, the sort of assumption, the sort of measurement error distribution being common for all these sources can be challenged. We might want to model these measurements with their own error distribution. And these are the kind of features that one might be able to use to explain the variability in the transit times. For instance, there are team drivers, which basically means they tag team. One drives while the other rests. There are different services that we can pay for. Some are more expedited than others. We have information about the driver, the company that they work for, and there are other things that we can engineer, like weather information, traffic information, temporal features, such as where we are relative to the current quarter, which we can use to hopefully explain some of the variability that we see in the data. So I want to tell you a story. This is my story of working on this project. This was our original MVP. We were doing exploratory data analysis, and part of that is fitting basic models, see what progress you can make. And in the effort of adding value to the company as quickly as we can, if we can improve what currently exists, then why not release that as an MVP? So one of the models that we tried first was an ensemble of trees kind of method trained by the XGBoost software, which is a pleasure to use. And compared to the existing predictive service, we apparently were doing very well. So this is a histogram of the residuals. And orange is the histogram of the predictive error of the original predictive service. And then the predictive error is shown in the blue histogram from the new model. And so we can see that the features were able to explain the variability in the data. The distribution of our residuals is more concentrated around 0. And so we thought, job's done. But much like life, it's not so simple. When we communicated to the stakeholders, one of the most interesting feedback we had was talking to the engineers, and they said, what does your model consume to make these predictions? And they said, those inputs, they're just not available at the time when we want to make predictions. For instance, if we imagine the final leg, that car hasn't been assigned to a driver yet. Actually, we don't know all of these features at the outset when we want to make predictions. So actually, this problem becomes less of a regression problem, more of a density estimation problem. We'd still like to learn the distribution of transit times and model that uncertainty, and then make decisions that are optimal under some loss function in the presence of that uncertainty. The other great bit of feedback we got was from logistics. They said that these transit times, they just don't make sense. I know, because I am a domain expert, that that edge takes, say, 6 days, and your model is saying something which I know not to be true. So you can imagine it's quite embarrassing for me at this point when I've just given them this model. And what that meant is that actually the data that we were training on was not good training data. Our model explained the training data very well, but people are disagreeing that this data is a good representation of reality. And there's hypothetical situations where you can imagine that if a driver is marking something in transit, they might forget until they're halfway down the road. They might remember and then mark it in transit. That's not the true in-transit time. Similarly, some car might get delivered at a hub, and it might actually not get checked in by the worker until some time after. So these are all sort of like human errors, and there's also a lot of post-processing that goes on with the raw data. We tried very hard giving each of these sources their own kind of error distribution, debiasing it with regression components, having heavy-tailed error distributions to mitigate the influence of outliers, but it was no hope. So this was a classic case of garbage in, garbage out. These were very dark times for this project and difficult conversations with my PM. So I've learned that sometimes, as a data scientist, you need to go beyond using the data that you're given. I have a friend who's a doctor, and I asked him why he had such a crazy long kind of work schedule, like 36 hours or something. And he said that they kind of want the same doctor to do the diagnosis and then the treatment and then the follow-up, because they want to be with the patient throughout the whole lifetime. They want that continuity. And I think that analogy actually extends to data science. It's really good if you're involved with the collection of the data, and then the processing steps, and then also the analysis. So I think if there are any recruiters in the audience, these are the kind of things you want from a candidate. You want someone to know what data is relevant to collect, someone who can actually practically implement that data collection and storage, and then someone who can actually do something with it, do the analysis, and build the predictive models. So we decided in our team, we're going to get our own data. So around each of the facilities in the network, we can define a spatial polygon, which we're going to call a geofence, okay? And periodically, we can request the GPS location of the car. So these are indicated by the black pins here. And we can see that when we query the GPS location of the car, we get a timestamp. And we can see that it's actually in the origin geofence, the geofence associated with the origin node. So we know that the car is inside that node at that time. And then the next ping we get is when the car is outside of the geofence. And so we know that the car had to have departed within that interval of time. It's not a direct measurement, but we are confident that it left at some point in that interval. By the way, that geofence down the bottom is this hotel. So that's hypothetical. Similarly for the arrival time, right? What we can do is we can look at the latest time that it was outside of the arrival geofence. That's a lower bound on the arrival time. And we can look at the earliest time we had from the car inside the destination geofence. That's an upper bound on the arrival time. So our raw data kind of looks something like this. On the x-axis is time, and on the y-axis, we have a discrete set of VINs. So let's just look at the top one. And a VIN is a unique identifier for a car. If you move your eyes to the right, you have the first event, which is a lower bound on the in-transit timestamp. And the next one you get is an upper bound on the arrival timestamp. So the car had to have actually departed its origin within that interval. Similarly, we have something for the arrival timestamp. So with just some subtractions, what we get is training data that look like this. For the transit time, we have a lower bound on how long it took, and we also have an upper bound on how long it took. In the statistics literature, this is called interval censoring of your observations. And if you work in survival analysis, this is really your bread and butter. So how does one build models from interval censored data? Well, let's just start with a basic model to introduce this idea. Let's model these transit times and dwell times as log normal random variables. I mean, they're positive, so the distribution has to be positively supported. And we're going to put a normal inverse chi-squared prior on the parameters. So this is where things get Bayesian. And the nice thing about this is actually defined by the existing predictive service. And this really helps us sell our work at supply chain automation, because the nice thing about this is that it gracefully defaults back to the prediction made by the existing service in edges that have low sample size. Okay? So there's that added security that if you have low sort of sample size for your training data, then your prediction is basically what's currently in place. And people like that security. And it's really good when you're trying to automate things. It's better to try and build on something that exists rather than completely replace a service. And we observe that our observations are interval censored. So the trick here is that the posterior distribution of the parameters, conditional on those intervals, can be recognized as the marginal from some higher dimensional joint distribution. And the nice thing about the higher dimensional joint distribution is that it has an analytically tractable conditional distributions. What we're doing is we're actually reintroducing the actual transit time as a parameter to be learned. So we're introducing that back into the model. And then conditional on the interval censoring in the parameters, it's a truncated normal distribution. And then the parameters conditional on the unobserved data is a normal inverse chi-squared distribution due to conditional conjugacy of this prior. So you may not be surprised to see an application of the EM algorithm in this missing data context. This is an optimization algorithm which we can use to train the parameters. It's scalable, which is good when you have a lot of data. And there's a lot of statements that you can make about this theoretically, which are very useful for writing unit tests. If the lack of purity in getting point estimates makes you embarrassed among your Bayesian friends, you can also do Gibbs sampling. Or, you know, it doesn't have to be Gibbs sampling, but MCMC. But for this model, the Gibbs sampler is pretty easy to set up. So here's a sort of example data set. We have 100 kind of interval-censored observations. The red is the upper bound, black is the lower bound. And we're trying to learn the distribution of these transit times. So with the EM algorithm, you get the nice unit testable property that is always increasing the log posterior at each iteration. So that's great for writing unit tests. You also have the optimality criterion that the derivative of the log posterior with respect to your parameters should be the null vector at optimality, so you can terminate when that falls within some tolerance. And then you can see the parameters converging in the parameter space on the right. And this gives you a transit time of about 7 days with a standard deviation of just under 0.4 days. Alternatively, if you do Gibbs sampling, this is the output that you get. You get trace plots of your parameters, and you can use these to summarize the posterior distribution, in particularly in the bottom right, we have the posterior predictive density, which is the distribution of a new transit time. And this is much more information than just a single point estimate. Now, the previous assumption about modeling these as a log normal could potentially be challenged. This parametric model might not be flexible enough to appropriately model the data. So that was kind of our MVP, and now we can sort of begin to do a few more fun things. So towards something a bit more flexible, we can, in a sense, generalize the previous model, which modeled the logarithm of these transit times as a Gaussian. Now we're going to model them as a mixture of Gaussians. And in particular, we're going to use a Dirichlet process mixture of Gaussians, where the base measure is the prior that we just used previously. I won't put the algorithm here for doing this, but it's MCMC. It's in the references. It's a slight modification of algorithm number 3 from a paper by Radford Neal in 2000, with an additional step to impute these censored observations. So if you run your algorithm, at every iteration, you get a new estimate of the distribution. So some people who work with time to event data like to look at the survival function. So the black is the posterior mean of the estimate of what this function looks like. And the dashed lines are 95% posterior credible intervals. And what the survival function tells you is the probability that a transit time will take longer than something. So this gives you a handle on sort of like when you should start to flag things. It's useful for generating alerts. What's perhaps more interesting is looking at the estimated density. So we're doing density estimation. We're not getting a point estimate out. We're getting an entire distribution out. And so this is for a particular dwell. And what we see that the dwell time within that node is not a unimodal distribution, it's a bimodal distribution. And what that tells you is sometimes the dwell is 0.6 days and sometimes it's 1 day. Now, there might be a feature that could explain the membership of a data point to one of these two modes, but that's a feature that we don't have when we're trying to make prediction. So what we need to do is we need to be able to include this uncertainty when we're making decisions. And so when we talk to stakeholders, they say, how do I use this distribution? I need to have an ETA. I need a point estimate. The problem with reporting a point estimate is it contains a lot less information than the entire predictive distribution. In the previous case, what would you have given them? Would you have given them 0.6? Would you have given them 1? Or somewhere in between? All three of these would actually be wrong. The predictive distribution contains much more information than just reporting a point estimate. And what we get out is the posterior predictive distribution. This is the probability distribution, which expresses our belief about how long a transit is going to take. And when we talk to the stakeholders, the reason why they want a point estimate is to make a decision, basically. And the decision is different, depending on what team you're working with. But one of them, which is easiest to illustrate, is someone has to schedule the customer to come pick up their car. So they want to know, when's it going to arrive so I can schedule the customer. And then when you begin to talk this problem through, it's like, what is influencing your decision here? Well, if the car arrives late, then the customer has to be rescheduled, and that's damaging to the brand. And you ask them, what is the KPI by which our new service is going to be evaluated? And some people will say, well, we don't want to have any reschedules. So it's very easy to give a model which performs amazingly under this KPI the whole time. Just add a really large buffer. Schedule customers a year after the car arrives, right? There'll be no reschedules. Problem with that is you've got all these cars sitting around, and that also has some loss to Tesla, okay? There are storage costs. There are working capital costs. We can't book this revenue until the car's been delivered. So ideally, we'd like things not to be sitting around, but not to reschedule the customer. And it's also interesting because you talk with different teams and they say, I don't want any cars to be early because I don't know where to put these cars. And I don't want any cars to be late because I don't want to reschedule the customer. So what we have is a loss function, and this has two inputs. One is when you schedule the customer to pick it up, and one is when the car arrives. And working out what this loss function is actually a really interesting analytics effort. So we have things like customer satisfaction data. You know, they do a survey like 1 star, 5 star, how did we do? And we also know if the pickup time was rescheduled due to the car not arriving. So you can actually do an ordinal regression to measure that effect of that factor. You can talk with other teams, and they'll say, well, a loss of 1 star causes a loss of this dollar amount. So you can actually put a dollar amount on what that loss is. And similarly, working with, sort of where the cars are stored and the working capital costs, you can actually work out what this loss function should look like, or at least qualitatively what the behavior should be. Can't tell you what it is. But you want to choose the decision to minimize this loss. The problem is that it depends on something uncertain, which is the car arrival time, this Y star. So what's the appropriate thing to do? Well, we have this posterior distribution of when we think it's going to arrive. We're going to compute our expected loss, and then we choose the action to minimize our risk, the action which minimizes our expected loss. So actually, that's all I have to present to you today. It's sort of showing you how you might approach this problem in a Bayesian way and start to think about a decision theoretic approach to sort of drive operational change within the business. Modeling these distributions is both providing predictions, but there's also like a feedback loop. For instance, if you learn this distribution and you find there's a lot of uncertainty along some edges, you can talk to people and say, what is the behavior in this hub? Why is it so uncertain? And is there extra information that we can collect to actually reduce uncertainty? So a large part of the effort is, what data can we collect to reduce uncertainty in our predictions? So I appreciate the text is a little bit small, but the slides are available, so these are the references. And thanks for attending.